Hi, my name is Joseph Rivera. This is Nicole Orndorff, Vincent Jang, and our cameraman Mohammed Alisa, and we are Team 23 Newton's BRG. So for this design phase, we were finishing up the rest of the Gantt chart. Throughout the whole project, we tried to follow the Gantt chart as accurate as possible, but due to some time constraints, we did have to lengthen some tasks. For example, prototyping, we actually had to shorten tasks by a few days because it took a lot shorter to complete the task because our overall design was very simple. Throughout the whole project, the Gantt chart served as a very good organizational tool for our team. We reference it many times when working on tasks and see what we're behind and what ahead on, so we can adjust our progress accordingly.
In DP3, we looked at environmental factors. Specifically, had different goals. We looked at potential environmental impacts, and we also looked at future guidelines we could implement. For one of our major goals was extending the useful product life, and we did this by choosing materials that were durable and would make our BRG last for a long time. For potential environmental impact, one I wanted to point out was waste generation during production and also waste generation from packaging and recovery process. We feel that this is something that we could focus on in the future of reducing waste generation with our BRG. And for guidelines we were looking to implement in the future, one would be specifying lightweight materials so that our packaging would, again, reduce waste by being lighter and having less packaging materials. Additionally, we would want to implement reusable platforms and materials, which we do. Our BRG comes in many separate parts that could easily be replaced, such as an LED. If it burns out, you can easily find one, purchase it for very low cost.
So we ran a failure modes and effects analysis on the entire BRG. Because of our conservative design, most of the risk priority numbers were very low, most of them less than 100. Here I'm going to go into more depth on the one that didn't follow this trend. This one had a risk priority number of 288. So the item associated with this failure is the projectile ramps, which are obstacle 3. The potential failure is that there's too much spacing between the ramps, and the potential effect is that the ping pong ball doesn't make it to the next obstacle. The cause of this failure here is that there's miscalculation of ramp separation, and how we're going to sort of avoid this is we're going to provide the students with all the kinematic equations needed to calculate the accurate distance. Given that they miscalculate this distance, they will realize that and adjust accordingly, and that's sort of part of the whole learning process of the BRG.
In this design phase, we also considered several different industrial design factors. Specifically, quality of the user interface, we gave it a high performance rating. This is due to Arduino being user-friendly and having an easy interface that the students would be able to learn. Additionally, all of our product comes with detailed instructions that will help guide students through the process. For emotional appeal, we had a relatively mid-range score. This is due to the fact that we think that our customers will be happy with our product. However, it is a low-cost product and it's not as expensive, for example, as an iPhone, which is definitely more exciting and has more emotional appeal. For the ability to maintain and repair the product, we have a high performance rating. This is due to the fact that all of our parts in the BRG are interchangeable and easily replaceable. For appropriate use of resources, we have a relatively high rating. Again, this is due to the materials we chose for our design being lightweight and easy to use. And for product differentiation, we have a relatively low score. This is due to the fact that a Rube Goldberg device has been in market for a long time. It's very common and most people know what it is, so it's hard to have our product be differentiating compared to a lot of other products on the market.
So our product architecture, we decided to use a modular model that creates a linear flow. So that means there's like the parts are not crossover together, and the other users can like change each of the parts easily without changing the entire product. So with that said, our product are separated into different 5 different chunks, which are the first one, spring as an initializer, and the second one is a entrance ramp and the ground as the base, and the third one is the projector wrap. That has a director to give the direction of the ball, and the third chunk is the dominoes, which has a communicator that communicates the previous obstacle, and the last one. So for the last one, it's all general sensor with the speech and the exit ramp. That actually acts as an indicator that indicates the end of the the flow.
Our economics analysis started with the assembly time of the entire BRG. Um, as you can see here, our more complex obstacles such as the projectile ramps had a lot longer assembly times because of their large difficulties in rotation. So you have the ramps at 1.95. But the overall BRG is predicted to be about 32.43 seconds, which is a very reasonable time. For our bill of materials, we had to choose a material that was very durable because we didn't want that many repairs being done. So we used injection molding and polypropylene as our material choice. So we decided to use injection molding on everything except for the frictional surface, the Arduino, and the spring, and we looked to outside companies for deals and getting things at much more reasonable price so we can sell our BRGs for still a low price. Our overall cost is $30 to manufacture, which is very reasonable and very cost effective since we plan on selling our BRGs for about $50.
So we used Inventor to create 3D and 2D models that were used to help us visualize and manufacture the final product. Here you can see 2D models of the final BRG, including some of the dimensions. This greatly helped us when we were actually assembling the final BRG. In the next slide, you can see the 3D model of the final BRG with all the labels. Here we have the initial launch system, to the initial ramp, to the projectile ramps, to the frictional surface, hitting the dominoes, and finally turning on the LED light. So, in conclusion, things we wish we could have done differently. We wish we could have ran some sort of stress analysis on either one obstacle or the entire BRG. Another thing is we would have liked to include some sort of circular loop. But with that being said, we were able to successfully design and construct the BRG, as you can see by this video here. With that being said, this concludes our DP3 presentation. Thank you for watching.